Hello everyone, good morning. Welcome to the class ECE451, the control engineering. Today this lecture is for the 14th week, Monday's class. Right. ECE451. This semester almost done, right? We have totally 16 weeks, and now is the 14th week. In this week, we were 14th week. Today, the Monday, we gave some new material, and then Wednesday will be just a review. Okay, this is review for the final review of the whole semester. Then we will go to in the 15th week. No class. Yeah, for the okay. Here's a holiday, right? We have holiday. We have the Thanksgiving Day. Then the 15th week, no classes. I use this week for office hour. We have Monday's office hour from 4 to 5 p.m. and also Monday and Wednesday during the class time there will be 9:30 to 10:45 is a.m. Right? We use these for office hours. And then the 16th week will be final exam. Which day? Tuesday, I think. Then we'll go online. They have the schedule. The university put the schedule online. Schedule. No. Schedule. Exam schedule. Final exam schedule is for 2020. So from December 7th to December 11th. December 7th is here. Okay. Our class is on meeting on Monday or Wednesday or Friday. And we start from 9:30, right? Our class actually start from 9:30. So, yeah, it's Tuesday. Always evening? I think they put it wrong. Or is it PM? Oh, 12:30 is PM. Yeah, that's 10:30 is AM. Okay. Yeah, so okay, let me copy this. It's Tuesday 10:30 a.m. to 12:30 p.m. Yeah, it looks like start from p.m. not p.m. Yeah, 10:30 is a.m. So 30 is p.m. 12:30 is p.m. Okay. Yeah, sometimes I feel confused, like 12 o'clock in the noon. It is AM or PM? I don't know. I just say noon maybe. Okay, this is the time. This is the exam time. Tuesday will be December. Which day? This is 7 to 11, right? 7 to 11. That's here. December 7th is Monday, so 8th. December 8th is Tuesday, right? December 8th. December 8th, Tuesday. This is exam time. All right. Okay. Then let's go to today's material. It's still in the digital control, right? We have several methods for the digital control. We have some I say like some P of S. Yeah, maybe this is a controller, maybe it is a sensor or whatever, some part of the whole system. We want to realize these in a digital way. Suppose this side is R of t, this side is some V of t. We want to realize in a digital way, then it will work like this. You start from R of t, but then you will transfer from analog to digital signal to like I say, it's RD of n, and then we have a PD of S, PD of Z. Is a discrete time system. We have transfer function is given use a Z for the variable, and then we have some VD of n. Okay, then this one we do a reverse convert from digital to analog. Then we have V of t, I say V hat of t, and we want like a Vt equal to or very close to V hat t, and things like this. So this is the digital one. This is digital one. Digital, right? We realize it digital. Okay, then this part how to choose? Oh, I need a T, right? I need a kind of like a switch, clock controller switch, right? You get a T. Now how to realize it? We have several methods. The first one is a testing method. Another name is a bilinear method. A linear method. We just transfer. We change this S to be P of here's a 2 over T, Z minus 1 over Z plus 1. I replace S by this part. That's it. So this one is PD. This one is PD. Okay. This is one method. And another method is matched pole 0 method. You can write as as MPZ method. This method we have 3 steps. The first step, we change all the poles. Poles are zeros. Poles are zeros to be the like a poles are zeros. We have S plus A term. Then this A will be the negative A will be either pole or 0, depending on this part is in numerator or denominator, right? We have this one. For this one, we have there is a term 1 minus e to the negative az, z to negative 1. Now we have this one in the PD of z. This one, for this one in the PS is PS. For this term in PS, then we have this term in PDZ. And second step, we need to check the order. If the order of the numerator smaller than the order of the denominator are not equal, smaller, then add a term, maybe several terms. The term is z plus 1 term. Add z plus 1 terms on the numerator. Until until order of numerator equal to the order of denominator. Writing this way. Alright. Then the third one, we want the final value. Must be same. Must be same. That will be limit s tend to be 0. Here's a g of s. You can say this is just g of 0, right? G of 0. But of course, for some kind of transfer function, you cannot have this, but you can have limit, things like that. And this one we want equal to limit z go to 1. This is also the final value for discrete time system. Here is a 1. Let me see. I need a 1 minus z to negative 1 times g of z and divide by, okay, just like this. It's a g of z, gd of z. It's like this. Alright. Yeah, you check the textbook for the formula. I think it's good. Okay, so we will check this. Usually you can calculate this just by gd of 1. You plug in z equal to 1, then you can have this value. But some case you have to do the limit. Okay. So after this, we can have a field. This is a match the pole 0 method. Alright, today I gave you 2 more new methods. So one is okay, I think this is a 1. Now this is 1. This is 1. This is 2. Then we consider we have third method. Third method. It is modify that one that is MPZ method. This is a modified MPZ method. The match the pole 0 method. This one is just a similar ways step 1 and 3 are as same as MPZ, but in step 2 we will add the term z plus 1 term to the numerator. Until the order, the degree of the numerator smaller than not smaller, equal to the degree of the denominator minus 1. So minus 1. And this one we want they are same. We want they are same. If it's not same, we add more terms in the numerator. Now as we want they have one different. They can have one different. But of course, if the system is already in the form, numerator has the order is is reach this one or even larger, then you do not need adding any more z plus 1. Okay, this is a method 3. And method 4 is also a pole match to pole method, but we do not consider z. Like here, the match the pole and 0 method, for both pole and 0, this kind of things will be replaced by this one, right? And now we only do this for numerator. But before we do it, we suppose this one. We do I show several steps. Step 1. By partial fraction, we have that function p of s, right? P of s will equal to some a1 over s minus p1, a2 over s minus p2, until a n over s minus pn. Yeah. Suppose we write in the by partial fraction, we have this one. Then we have p d of z. It is I replace the denominator by similar with this. Here I write is s plus a. Okay, there s plus a. So here will be 1 minus e to the, here's a negative at, now it's just a p1t, the z to negative 1. Okay. Here I use z, sorry. Let me see. Here I have a term z. Yeah, here's I added this one is s plus a z to z minus to this term. I'm sorry. Yeah, to this term. And then in numerator we need add this. Okay. This is the MPZ and the MMPZ method. This is MMPZ method. Modified MPZ method. And now we replace the denominator by this one. And the A1 is still A1. A2 is still A2. P2T z to negative 1. Until an over 1 minus e pnt z to negative 1. But after all of these, we need a times t. So this is also a method. What's the name? This is it's an impulse invariance method. Invariance method. Okay, let's study an example. Okay, example. You use P of S. This is a system. We want to find the digital one for this. Try to realize in digital way. And okay, I suppose I use the s plus 2, s plus 3, and here's like a 6. Okay, just 6. Yeah, we use this as an example. This as an example. Then we want to find the digital one. For digital one, we have different way, right? The first one, digital one. So the first one we can use we say PD1 of z. There will be 6 over s plus 2, s plus 3, but s will be replaced by 2 over t times z minus 1 over z plus 1. T, which can choose a t. T, for example, 0.1. Right. And the second method, this is a modified. Second method is just MPZ method, right? MPZ. This is a testing method, and this is a MPZ method. MPZ method. PD2 of z equal to. Okay, here we have two factors. Each factor will be replaced by z minus e to the negative 2t times z to negative 1, just times this, and z minus e to the negative 3t. This is numerator. And denominator, I need a z plus 1 with a square. I need to add some z plus 1 terms, make the numerator and denominator, they have same order, so add this one. And then I need a times k in front of it. Now what is a k? K will be determined by the final value. The final value, this one is 1, right? So P0 or equal to, okay, I put a C here, okay, PC0 or equal to PD2 of 1 to give k. So this is just 1, right? 6 over 2 times 3. And this side, it will be 1 minus these. It is a k times, this is 1 plus 1 is a 2 square over 1 minus e to negative 2t and 1 minus e to negative 3t. This is the whole numerator, whole denominator. So k will be 1 minus e to negative 2t and 1 minus e to negative 3t over 4. So I have this k. I have this k. Alright. This is the second method. And the third method, I have modified MPZ. Modified MPZ. Then this PD, I say P3 of z, it will be, okay, denominator is same. It's still z minus e to negative 2t and z minus e to negative 3t. And here will be some k times z plus 1. Okay, just z plus 1. Just z plus 1. The order, denominator I have order 2. So numerator I have 1 less, it should be order 1. So 1 term will be enough. Okay, then this time I still determine k. I have 1 equal to, this is a P0. Okay, I should write one more. PC, when s equal to 0, equal to BD3 at z is 1. So this is 1 equal to, this side is a k times 2 and 1 minus e to negative 2t and 1 minus e to the negative 3t. Okay, the k just this one over 2. Right, this is k. Okay, and then we have the, I give you one more method, right? The fourth method. The fourth method is impulse invariance. Impulse invariance method. Impulse invariance method, we need to write the piece continuous system as I have now is the systems here, right? Systems here. We perform partial fraction. So this is a over s plus 2 and b over s plus 3. I want a times this plus b times this, get 6. So, oh, I did this last time, right? Did I? Yeah. Okay. So this is a 6 over s plus 2 minus 6 over s plus 3, right? Yeah. So I have this one. Okay. Then this one I will replace the denominator similar with this, similar with previous one, but we only we do this replacement for each term. So this is a PD. This is the fourth one. Z equal to. Okay, this is a 6 over s plus 2. Now is a z minus e to the negative 2t. If we already have this term, this one is the same way the MMPZ, but now we do it for every term. Just every term, just a constant over s plus 2 or over plus 3, right? And minus 6, and here's a z minus e to the negative 3t. So you can say that this method is just the MMPZ, a combine of MMPZ. MMPZ, you can apply it everywhere. This one, you apply it for each part. Then you combine together. But mentioned by this way, if you just combine together, you the same way with MMPZ, they are not exactly the same. Here's a partial fraction you separate, and you working this way. When you combine these two together, you will not go back to this part. Will not go back to this one. They're different actually. Okay, and also we need a constant k, and in this case the constant, it is just t. It's just t. All right. Okay, this is the fourth method. Now we can try to run it in MATLAB. Okay. Okay. MATLAB. ECE451. What kind of files we have here? Let us edit ECE451. This is for the 14th week, Monday's class. Okay, edit this one. These, and let me write code here. Okay, so we have the example. Examples here, right? We have how to define this one. I use s equal to the transfer function of s just for s. Then we can have PC, the continuous one. They are equal to 6 over s plus 2 and over s plus 3. Now here you cannot put times. This you put times, that means times the overall, times the whole thing. Actually this times happen in the denominator. It is 6 over s plus 3. Okay? So it's over and over again. Over s plus 2, then over s plus 3. Okay, so this is PC. And then we will replace s by this one. So I define the z, and define the z. What happened? Yeah, click my mouse, touch something. Okay, I define the z, which is a transfer function. Now is a z with a ts, with a t. With a t is I put it in the front. T the step to take the sample. T the step to take sample. For example, I use 0.1. Yeah, you can put any value here. After we finish the whole program, we can choose different t to see what happens. Okay, this is a z equal to this, and then I will replace s by s. For example, I denoted s is sz. This is 2 over t, then times s plus times z minus 1, and divided by z plus 1. This is a bilinear transform, right? Bilinear approximate. I replace S by this part. Okay, then PD1 will be just the same with these. Okay, same with these. However, we need to replace S by SZ. Alright, so this is PD2. Let's run it firstly. Have a look whether it's good. Save. Yeah, it's slow. Is it running? Something wrong? Oh, nothing happened. Yeah, I don't have graph yet. Okay, I put the step figure 1, then hold on, step of P, the continuous one, and step of the P digital, the first one. Okay. All right, yeah, the step response. All right, they are quite fine, quite good. And before that, I put the glow. Oh, so all the graph will be closed. Okay, this is second one, PD1. I put this is the continuous one. This is a digital with testing method. And then we do the second one. MPZ. We need to have these, right? You need to have these. So we need a K. I write K firstly. Okay, K is here. K equal to 1 minus exponential power of -2 times t, and times 1 minus exponential power -3 times t. Alright, this is numerator. And divide by 4. This give us K. Then P, the digital, the second one, which is a MPZ method, it will be K times. So here's a Z plus 1 squared and over Z minus exponential power -2 times t, and over another Z minus exponential power -3 times t. Am I good? I don't know. Okay, but I can double check and check the step of PD2. Alright. This case they are same. P1, P2. It should be a little bit small different. You see? Yeah. We have 2 digital ones. One is in color green, one is in color red. They are not exactly same, but quite similar, right? Quite similar. Okay, so this is a step response of these 2 PD, and we have the third one. Third one is MMPZ. Okay, so MMPZ, this is PD2, then MMPZ is somehow similar with these. Let me copy it. Okay, I have different K. Now is this one times this one, but over 2. Over 2. And then PD3. There will be K times Z plus 1, just plus 1, no square. The denominator same. Alright, this is PD3. We can have step PD3. Alright, let's run it. 3, put them together. We have 3 of them. Can we, like here, can you see? Yeah, we have 3. The green and the red curves, they are PD1 and the PD2. This PD3 is this one. It's light blue. Right? It's kind of blue, light blue. Okay, so this is the third one. And then we have the fourth one. Fourth one is also similar like these. I need to use this one. Now is 6 over, okay, it is a 6 over, the K is just T. This time K is just T. And it is 6 over Z minus these plus 6 over Z minus these, and K is totally outside. K is just T. Okay, this is another one, PD4. Okay, then I put this is out here, PD4. Step PD4. Okay, let me run it. Oh, this one I don't need times T. At times T is going down. PD4, which one? This is PD4, too large. If I remove this, oh, even large. Oh, so I need a T. Let me see. If T times it, here's 1, here's close to 6, or maybe I don't need a 6. So I get something wrong. If I remove the 6, 6 will be 1, what do I have? Function. I get something wrong. Oh, here will be minus. Okay, yeah, here should be minus. Let me see here. Sorry. This should be 1. Here's a Z to negative 1. Here should be 1. Here's a Z to negative 1. Okay. Now it should be like this. Here's a 1. It should be 6. It is 6. 6, not Z. It should be 1. And here's a Z to negative 1. That means divide by Z. And here's a minus 6. And here's 1. And here's a Z to negative 1 over Z. Alright? Okay, let's run it. Okay, this time is good. Alright? Let's enlarge. Yeah, we have 4 different ways to do the digital controller. We can have a look anywhere, like here. You can see we have 1, 2, 3, 4 different ways. 4 different ways. Yeah, at like here. Right here we have 4 different this green, red, this is a light blue, this is a purple, right? We have four different, yeah, 4 different way for the digital control. All right. Okay, so this is a step response. We can also see the frequency response, right? We can also see the frequency response. Frequency response, let me give another graph. This is figure 1. Then let me give a figure 2. And now it's a frequency response. I use both plot. Okay, both plot of PC, and both plot of PD1. I can copy this. 1, 2, 3, 4. Right. Need a 1, 2, 3, and 4. Okay, 1, 2, 3, 4. Let's run it. Okay. Yeah, this is step response, and this is a spectrum. The both plot. You can see in the low frequency part, they are fine. And for discrete time signal, the highest frequency is just here. It should be 2 pi. Now we take sample t, so the frequency, you think the frequency should be pi t, pi over t. Let me see. Let me write something about the bold plot. Bold plot. We have PC. It looks like something looks like this one, and here's a like this. Here's a 0 dB, right? And this will be negative something, and this will be 0 to, that'll be 180. I think here's a 180. Right, this is PC, and okay, here's omega. Omega could be odd number, and PD 1 and the PD until PD4. They're discrete time signal. So here here is just pi over t, the frequency, the maximum value is just pi over t. Okay, yeah, sorry, I lost that part. Yeah, so both plot for PC, it looks like this, right? 0 to 180. I just copied from the graph, and yeah, I can show both. This one, right? It's a both plot, and this one, this is a pi over t. Highest frequency is pi over t. Why is it pi over t? You can see in the signal, you have 0t, 2t, 3t. You have value, right? You have some value. Then the highest frequency is what? In what case? T, 2t, 3t. Now here's a 1, negative 1, 1, negative 1. This is the highest frequency. Yeah, you cannot find the discrete time signal with a frequency even higher. Here's a t, every t, 2t, 3t. Then the period is period 2t. 2t, right? You see the frequency. We say frequency, high frequency. That means the signal jump up and down rapidly, right? High frequency, rapidly. And low frequency, it will coming from up. It will run up and down slowly. And this is the most rapidly, the rapidest, right? Most rapidly for discrete time case. Right? 1, negative 1, 1, negative 1. You cannot have even more rapidly, more high frequency than this. This is the highest frequency. And this is quite different between continuous signal and the discrete time signal. Continuous case, the frequency could be any large number, right? But for discrete time, this is the highest one. You cannot even have even higher. Okay, this case period is 2t. Then the frequency, there 1 over 2t in hertz, or 2 pi over 2t, which is pi over t in the radians per second. So here's a pi over t, pi over t. You can see the graph in both plot. Here's a 0, t0, 10, 0, 10. So this is 10, this is 20, this is 30 something. Actually 10 pi. Is a pi over 0.1, right? Or t is 0.1, so it's a 10 pi. This is the highest frequency here. All right, and the magnitude here will be, it is a, okay, this looks like this, like this, and the phase is also something looks like this, going down. This part, okay, the graph is it should be like this. So this part, this part, this part, this part, they are similar. They are similar. You see, this part, they are similar. This part, they are similar. But when the frequency coming up, the difference is large. And we have different methods. Each method they have different, different arrow in this part. In this part. Can we see more details? Make it large. Yeah, here I have only 3. How many? I get 1, 2, 3. I have 4. So other than the continuous one, I should have 4 of it. Okay, so maybe some of them they merge it very good. I can separate them. There should be 4 different digital one. Let me run again. There should be 4, right? But I can only find 3, or maybe see 1, 2, 3, 4. Okay, if for example I times these, the bold plot, I times this by 2, what do I have? Times 2, there will be a shift, right? Shift. After log, it will be a shift. Which one will shift it? I don't have the last one. Oh, the bold plot. Can I have bold plot? I can't. I times 2, nothing change. I times 100. This one. Yeah, I have 1 coming up. 1 up, 2 here. Yeah, 1. Okay, so 1 of it is combined totally same way somewhat. Anyway, so this is the bold plot, the frequency response. Okay, the frequency response. So in some cases you want to check the frequency response rate. Then you can also see. After you do the digital one, the low frequency part, they are quite good, quite close to the original analog system. But for the high frequency part, they have somehow larger, the arrow tend to be larger. Yeah. It's approximate. This is you go to the digital one from continuous to discrete time. Of course, you will have some error. Yeah. Okay. All right. For the digital control, I only want to discuss these several methods. This should be more. It should more, and you can also read the textbook. I think they also have more than what I gave here. C to D. Actually, they have a built-in function C to D in MATLAB. C to D. We can transfer a system in C, that's in continuous, with some step T with certain method to get a digital system, discrete time system. And the method here we have 1, 2, 3, 4, 5 method. The testing method is a bilinear method, right? We discussed it. And the matched method, actually this is a modified matched pole and zero method. Okay, so this is for the matched MPZ method. And the MPZ method is not discussed here. ZOH, this is zero hold on input. FOH, this is a linear exploration and input. So these two methods, that means in the input side, before you do the digital way, you do some change. Yeah, you do some like zero order or the interpolation. Yeah, you do some work before you use the input value. Okay, and this is also a kind of testing method, but you need a you need a pretty rapid. I'm not so sure. I think ZOH you can have them in the textbook. Yeah. Oh, there's a no. Okay, the impulse invariance method is not here. They should have this function. They have this function, impulse invariance, impulse invariant, impulse this one, impulse invariance. Impulse invariance, impulse invariant. Every user. Okay, this one. Yeah, this is this function. Impulse invariance is this one. Yeah, you can also run these for the impulse invariance method. You know the numerator and denominator of the continuous time signal, and use the Fs. Fs is frequency, so there will be 1 over t here. And then you have the numerator and denominator in the z domain, and you need to use a filter BZAZ to define the function, define the system. Yeah, you can also use this one. Alright. Okay. I think that will be all for today, and also all of the whole semester. We do not have new materials. In the textbook, we have one more chapter, two more chapters. One is for nonlinear control, and then the last chapter is a kind of a case study. It's a control design, system design. You can think it's a case study. Yeah. If you are interested, you can read the last chapter. And for the nonlinear part, actually we have further more courses related. So if you have chance, you can take some nonlinear control courses later. All right. Okay, and that's all for today. Have a good weekend. Not weekend. I'm sorry. too early. Next time we need a review. Okay. All right, that's all for today. Bye bye.